Yeah, the idea here was to, because we have a lot of developers around here and people that write apps for these things, and you might not appreciate how these things work in terms of how we get data over the air and how we do it so efficiently and quickly and so on. And also the complexity of these devices is just absolutely incredible. And so I just want to give you some appreciation for the history of these things and a little bit about how they work. Okay, so I was originally going to do this both cellular and wireless LAN and walk you through 1G, 2G, 3G, 4G, and then also the wireless LAN stuff. And in order to do this in a way that's meaningful, because I'm assuming that you guys don't have the math, the signal processing background and whatever. I think I did a good job up through 2G. We're not going to get past 2G today. So you'll see why. At the end of this talk, if you think it's worthwhile, you can have me come back again and I'll finish up 3G and 4G. So let's go ahead and get started here. Okay. So this is just a little teaser chart. You can get these types of charts off the internet all the time, and it just shows a history from '07 to 12 of the growth of traffic on cellular devices. So the golden bars is voice, and the blue bars is data. The blue bars, of course, is the 3G and the 4G stuff that you guys that we ultimately want to get to. So I want to say a little bit about what I'm assuming you guys know, because you got to know something in order for us to have this conversation. And I'm going to try to keep it almost completely non-mathematical. I think I have one equation, but I expect that you know something about basic frequency concepts. I expect that you know that seconds is a unit of time, and that hertz is a unit of frequency, and hertz is inverse seconds, and therefore milliseconds is to kilohertz, microseconds is the inverse of megahertz, nanoseconds is the inverse of gigahertz, and so on. So that's just basic background information. And that you know something about frequency distributions. So you know that like hi-fi audio, you might know that has a bandwidth of 20 kilohertz, which, by the way, bandwidth does not mean data throughput. Bandwidth is a measurement of hertz. Okay, so we can have that discussion. It's not how much time you have available. Okay. Speech has a lower bandwidth. You can get by with pretty good speech with about a 4 or 5 kilohertz bandwidth. You should know, the basic concept of frequency channels, like your FM channels are, 88, 103 megahertz. And you should have this idea, not a precise idea, but an intuitive idea of what I'm going to call duality in the frequency domain, that things that vary rapidly in time correspond to wide bandwidth. Okay, so that's that. If you're comfortable with that, we should work. Okay, now. For this presentation, I'm going to be talking about one app, the original app, which was speech. How do you have telephone calls? And a lot of the things, it's just a real useful one to get the concepts, of course historically, the first one. But a lot of the concepts we're going to see are going to play right over into data communications as well. So when you look at something like this, a speech waveform, you see that it's streaming. Of course, it's continuous. You have a continuous stream of data, but it's bursty in nature, so you have words. You also have a voice activity, because if you're having a two-way conversation, usually only one person's talking at a time. So there's like 50% of the time a given user is quiet. Okay? It's tolerant to errors. You can screw up this signal to a certain degree, and you'll still be able to understand the speech. Okay? And it's also delay tolerant, so you can delay speech. You can have a two-way conversation easily with a delay of 1/3 of a second, and people won't notice. You start getting up to like a second, like if you go over a satellite link, quite often you have delays of a second. That gets harder, but 1/3 of a second easily. Okay, move on. Okay, so now just some basic modulation. And I'm doing all this with pictures. So the speech band, the baseband signal, baseband is just a term that we use. It just means the signal at the low frequency where the, the content is. So that's like the speech signal that goes up to 4 or 5 kilohertz. Okay? An RF carrier, all an RF carrier is a sine wave. It's a high frequency sine wave because you're putting it on an antenna and you're transmitting it over the air. Okay? So the simplest type of modulation is just modulate the amplitude of this carrier with this baseband signal. Modulation simply means embedding one signal into another signal. Okay? So this is nice. You can detect this with a very simple circuit called an envelope detector. So this historically was the first type of radio signal that, other than like dots and dashes. There's a variant of it which is basically says, hey, this AM signal, this amplitude modulated signal actually carries both the modulation information, but it also has this constant carrier in it, and you're transmitting that, and that uses power, and power is wasteful. I mean, power is capacity, is bits. We'll see a lot more of that later on. So if I subtract out the carrier from this, I end up with something called double sideband. It looks like this, and now you can see the envelope is sort of following the signal, but when the signal went negative somewhere around here, it crossed over, it rectified the signal. So this takes a little more complicated device in order to demodulate it. But at any rate, the big picture here, it's basically just AM. So we need to have this concept of amplitude modulation. In the frequency domain, if the baseband signal has a spectrum that looks like this, then the amplitude modulation has a spectrum that looks like this, where this is the carrier frequency, and that big arrow there in the center is supposed to represent the power of the carrier. With DSB, we've just gotten rid of that carrier here, and we're just transmitting the information containing part of the signal. Notice that, the spectrum itself is just the baseband signal translated and then flipped over like that. That's why it's called double sideband, because each one of these things is called a sideband. Okay, so that's just what the radio frequency modulation looks like. Okay. Now there's another type of modulation that's called frequency modulation, and it's pretty intuitive. Same thing as you're taking the baseband signal, but now instead of modulating the amplitude, you're modulating the frequency. And you can see that in here where the signal's high. I've got a higher frequency waveform. Where the signal is negative here, I've got a lower frequency waveform. What does it look like in the frequency domain? It looks just like DSB. Okay. Okay, now, there's your first mobile phone device. Okay, this is called the Mobile Telephone System, MTS, which was launched in 1947. It's a little expensive. These rates, 180 a month, $3 to $5 a call, that's in 2012 dollars. So I don't think you'd be doing too much texting on this thing. There were 25 channels, and the idea is you just had one tower per metropolitan area. And with this system, New York City could have a few thousand users. So that, there was even at those prices, there was a lot of demand for that system. So how does it work, okay? So basically, this has all the fundamental components, the basic components of a cellular system, with these magic letters MA. So you probably heard this: FDMA, TDMA, CDMA. All the MA means is multiple access, and all multiple access means is sharing a communications resource among multiple users. Okay, so in this case, I've got 1,000 users. How am I going to share 24 channels across 1,000 users? And the answer is you have a control channel. So this simple network introduces a major component of all modern cellular networks, which is a control plane. But the control is very simple. Basically, if you want to make a phone call, you get on the control channel and you say, I want to make a phone call. And on the control channel, the network, which is just one cell tower, responds and says, okay, I assign you to channel 3. Have your call. Okay? And you go on, and then when you're done, you terminate the call, so there's another exchange over the control channel. You release that channel, and then that channel is available for somebody else. So as long as not everybody's trying to call at the same time, this can work. Of course, sometimes a guy comes along on the control channel and says, I need a channel, and there's not one available, he gets blocked. So you got a statistical problem. How many users can you use how many users can you bill before they start getting mad at you because they're always getting blocked? Okay, so that problem has persisted for a while. But at any rate, this worked pretty good for a long time, right? 1947, the first cellular systems was launched when? In the 70s sometime? Maybe I have that on my next slide. But at any rate, you see the capacity problem. You only had 24 channels, and if you overload it with users, you're going to have angry users. Okay, so the first generation, the first G was analog telephone system. And the basic idea was to make it into a cellular system. Okay, so the brightness here is not coming through too well. But basically what you do is you take your channels and you divide them into groups. So you got your frequency channels, you divide them into groups. You divide your geographical area into cells. And then each cell, which is each color here, is a different group. So this is a reuse factor of 3. That means I have 3 groups of frequency channels. And I'm going to, the yellow here is all one group. The green is one group. The blue is one group. Here's a reuse factor 4. Okay? So the idea is that I can have my cell towers that are serving this cell with the blue group of channels. And yeah, these other cells over here are also using those channels, so they're going to interfere, but they're not right next to each other. So the whole idea of frequency reuse is that you have to have these reuse patterns so that adjacent cells don't share the same patterns. So, and a little detail here is that a tower actually serves 3 cells. And they have these things called sectors, and this is supposed to show the antenna pattern of each of the sectors. So you see these, you can see this is a tower serving 3 different cells, and here's a tower serving 3 different cells, like so. Okay, so now what we're doing is, what we were doing before with the original system is we had a frequency reuse system that was based on assigning channels to users on demand. Here we have a capacity that's described in terms of, bits per bandwidth per unit area now, because we're going to reuse the same frequencies over and over and over across a geographic region. So that's called spatial frequency reuse. Okay, so that gives us tremendous, geographically, that gives us a tremendous increase in the number of users we can have and the capacity that we can have. It introduces a number of complexities, though. Obviously, it introduces the problem of interference, inter-cell interference. So my blue cells over here are going to get interference from these cells up here. Now, lower power, hopefully it's not too bad, but still it's going to degrade the performance in here. And so we have to deal with that. And dealing with this inter-user interference, this is 90% of what the whole cellular problem is about. Okay? And the other thing is that, or is it doesn't say in this slide, maybe in the next slide, but at any rate, the control problem just got a whole lot harder. Okay, it used to be a user would get on the control channel and say, give me a channel, and you'd assign them a channel, and that'd be it. Okay? But now, you have to know where the users are. What if somebody from outside the network wants to call your cell phone? Well, the network has to say, where is this guy? Which tower do I connect with? Oh, I got that problem. The users are moving. I'm driving around. I go between cells. I want my phone call to continue and in a seamless fashion. That's called a handover. Okay? So there's a lot more control complexity that's going on. So I'm just waving my arms around about that because there's just no way I can get into the details of that. At any rate, here's some parameters. This is what the original AMPS phones looked like. They were called bricks. Anybody remember these things besides me and Tom? Okay. 800 megahertz bands. They used 30 kilohertz channels. So they had like 15 kilohertz of DSP. Well, actually, they used FM modulation. The reason why they use FM, I'll explain that in a few. I'll come back to that. Okay. It's called frequency division multiple access with cellular reuse, which is what I described. And here's what I was talking about before. The additional network control and the network complexity was introduced with this. It actually had a control channel that was a digital control channel, but it was controlling analog calls. Now, we want to get into the digital stuff because that's 2G and 3G and 4G. And data and everything. And to do that, the next about 10 slides, I'm going to give you a whirlwind tour of digital communications. And we have to start with Claude Shannon. How many people have heard of Claude Shannon? A couple of people, okay. How many people have heard of Alan Turing? A few more, okay. Claude Shannon is the Alan Turing of communication systems. We worship him, just as we should all worship Alan Turing, okay? He's famous for the invention of what's now called information theory. Information theory has two components to it: source coding and channel coding. We need both of them. And you have to have a basic understanding of what these two things are before we can actually go on and dig into how these digital systems work. And I'll get into some of that because there's some very interesting applications of information theory, even in 2G, okay? So source coding is basically taking the problem into, the basic problem is I've got a source. It's a voice call, or it's an internet stream, or it's a video stream, or it's a picture, or whatever the source is. I want to communicate that to a far place and have it appear at the far place as it was at the transmitter, okay? So first I have to do is turn it into bits. That's what source coding does. But I want to turn it into bits efficiently because the communications resource is expensive, and what you want to do is you want to strip the number of bits you need to transmit down to the bare minimum in order to efficiently utilize your expensive resource there. So a lot of this stuff you already know about. So like Huffman codes, zip-length codes, okay, this is what they use in zip files. That's a compression technique. It takes out all the redundancy, and so that's how zip files work. MPEG, JPEG, MP3, ACC, all these things are examples of source coding. So I'm not going to talk about these. I will talk about speech coding, which is a little different than all these. Then you have the second part, which is called channel coding. So now I'm going to take the bits, I've stripped them down to the bare minimum bits, and now I want to transmit them over a communications channel, but the communications channel has noise. It's got distortions. It's got interference on it. It's going to make errors, okay? So channel coding does the reverse, is it takes the raw information bits that I got from the source coder and it adds redundancy back in. But it adds redundancy back in a way that makes the communications more resilient. Okay, so I'm going to have a few slides on these two different concepts. And let's look at the waveform coding problem in particular, the speech problem, because it's going to give us a really interesting example. So speech, let's just say it has 4 kilohertz bandwidth. Okay? So the simplest way to turn a speech waveform, like that picture I showed earlier, into bits would be to sample it. Okay, well, we know how fast we have to sample. There's a Nyquist sampling theorem that says we have to sample at twice the highest bandwidth, which would be about 8 kilohertz. So 8 kilosamples per second. And then for each sample, now I don't have bits yet. Each time I sample that waveform, I have a voltage, a value, a real value, not bits. So then I'm going to run those voltages into an analog to digital converter and convert each real number into a finite set of bits, okay? So the old digital telephones, not the wireless ones, but the actual wireline telephones, did exactly that. They sampled at 8 kilosamples per second. Each sample was converted into 8 bits, an integer, okay? So the total data rate was 64 kilobits per second. So high quality, it's called toll quality speech, is roughly equivalent to a 64 kilobit per second data stream. So let's look at this. Here's a speech waveform again. And you can see here in the speech, it's bursty, just what I said. You know, these are different words that are going on here, okay? When you look at this, though, when you think about it, with speech, we don't have to exactly reproduce the waveform. The goal in speech is really to produce a waveform at the far end that the listener will recognize as speech, and not only just as speech, but as the speaker that he's talking to, so speaker identifiable. So let's unwrap this problem a little bit more. So this is the time waveform, so this would be like voltage as a function of time. This is what the frequency, there's a special name for this diagram I forgot, but it's frequency as a function of time. And when we look at it this way, we can see that a lot of the energy is down here in the lower frequencies. You look closer, you see that there seems to be, in frequency, there seems to be this rippling effect here. So there's multiples of some basic frequency here that's going on. What's all that about? Then there are these other parts which look like white noise. This even distribution across frequency is the hissing sound, the type white noise sound. So, you know, again, I don't have to exactly reproduce the white noise waveform. I mean, you know, tss is a hiss. So if I just say far in, do a hiss, and it goes, tss, you'll understand that, right? Well, this is exactly what the encoders do. In fact, it's based on this this glottal vocal tract model. So here's a picture of the vocal tract, and here it's called the larynx, or the vocal cords. And vocal cords are just two little flaps of skin, and you push air through them, and they go like this, poof, 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 at a given frequency. So they produce this basic raw waveform that looks like little pulses in time. Okay? And then that waveform is basically modulated by the vocal tract by the shape, you know, your tongue moves, your lips moves, there's the nasal path plays a part in everything. And so you're basically blowing these pulses through a pipe that has various cross-sectional areas. And if I model that pipe as being just discrete sections, not a perfect model, but you can see if I do discrete sections and have enough sections, it'll be pretty good, okay? Then what do I have to do to reproduce this waveform in a way that will be recognizable as speech? I have to know the glottis frequency, I have to know its power, and I have to have a representation for this vocal tract model. And that is, you know, the representation is going to be a digital filter, and there's a whole lot of signal processing that goes on behind this. But still, if I have 8 to 12 sections, then it's kind of like thinking of these as being reflection coefficients corresponding to the digital filter coefficients. So if I can calculate those coefficients, then all I have to do is transmit those coefficients, and then at the far end, I'll just reproduce this device. And I'll reproduce the filter with the filter coefficients, and I'll reproduce the glottis pulse and run that through the filter, and it'll produce a sound that's pretty much like the voice sound, or a piece of it, okay? And in fact, what it turns out that you just have to recompute these things about once every 20 milliseconds, and you end up with about 10 or 15 parameters every 20 milliseconds. So the encoders that do this is the typical, well, the one that whenever you make a phone call, you're probably using the AMR encoder. But usually it's between 5 and 12 kilobits per second. So remember what I told you about the sample data type approach gave us 64 kilobits per second. This approach is a lot lower data rate. In fact, the state of the art is they can get it down to like 200 bits per second and still have intelligible speech. It might not be user recognizable or speaker recognizable, but it's basically doing this. Now, obviously, I've glossed over a whole lot of details. Okay, so I'll just move on here. But that's the basic idea of how that works. Okay. All right, channel coding. Now, channel coding is a little harder to explain, although it does have a very good, very, very simple example. And so I'm just going to explain the example. Suppose I have a channel that transmits bits, bits in, bits out, and every now and then it makes a bit error. Well, one way that I can encode it is I can take a bit, in this case 0, I can just repeat it 3 times, and then transmit those 3 times, those bits over the channel, and okay, I got an error here. But that's okay, I can do majority logic decoding. I got 2 zeros and 1. Probably it was a 0. It's more likely that there was only 1 error. So I'll decode as 0, and that was what was sent, so it worked. It corrected 1 error over the channel. Okay, so that is the concept, the basic concept of adding diversity, okay? Or excuse me, of channel coding, okay? Now, just a couple parameters. What happens is we almost never use a code that is this simple. What we usually do is take a big block of data, and encode it to an even bigger block of data. And so K is the number of information bits that you're transmitting in each block. N is the total number of coded bits that you encode. And R, which is the key, is the code rate. So that's the number of information bits per coded bit. And in this case, it'll be always less than 1. Okay? So now if you think about it for a second, no matter what I put in here for this channel, okay, as long as there's some notion of independence of errors, whatever, I'll take the channel bit error rate and I'll reduce it by using this type of simple code. I can make it even smaller. How? Instead of repeating it 3 times, let's repeat it 5 times. Or let's repeat it 7 times. You can repeat it as many times as you want. But the problem is every time you do that, K is 1, and N is going 3, 5, 7. So every time I do it, what I'm doing is I'm reducing the rate of the code. And so it gets more and more expensive. And the rate of the code is obviously going to limit the overall transmission rate you get. But nonetheless, you can see the principle is that if I let the rate go to 0, I ought to be able to get rid of the errors altogether, which is true. But Shannon proved something much stronger. Shannon proved his Shannon channel coding theorem, which says that for any communications channel, there is a channel capacity, which we call C, such that for any rate less than C, there exists arbitrarily reliable codes. What that means is, in detail, pick a decoding error probability. Now, I'm not talking about bit error probability. I'm talking about the whole block. And really, we don't care about bit error probability. Because if I give you a file, and I say, look, there's 2 kilobits in this file, but there's a couple of bit errors. Now, depending on your application, you're going to say, well, a couple of bit errors somewhere in that, it's useless. Throw the whole file away. Okay? What you want, what I'm talking about, is the probability of any error within the entire block. Okay? So pick a number. 1 in 10. 1 in 100. 1 in 10 billion. There exists a code with a rate, arbitrary close to C, that will give you that error probability. Okay, so in other words, the code rate is not going to 0 in order to get arbitrary reliability. So this is a powerful theorem. Now, this is a standard additive noise channel for which you can actually work out the mathematical formula. So I think this is my only math here. Capacity equals the bandwidth of the channel times the log of 1 plus the signal noise ratio. I'm just put this up here because it's just like, yeah, I mean, you got to realize that if you, that bandwidth, the amount of hertz you have, is the amount of data, the data rate that you're going to be able to transmit over the channel has got to be proportional to bandwidth. Okay? And signal noise ratio. If it's a noisy channel, that's going to reduce your capacity. If it has a high signal noise ratio, it's going to increase your capacity. Okay, so it's just now the kicker here, though, is even though we have this theorem, realizing these really powerful codes has something that's been taking us 30 or 40 years of research. And today, we do really powerful codes in wireless communications. But having this concept, now that I have this in place, I'm almost ready to talk about 2G. Oh, good. But we have to talk about data modulation, and we have to talk about the nature of the channel. So now, data modulation, this is just a base, this is all down at baseband. It's like, how do I take a stream of bits and turn them into a waveform? Well, the simplest way, the basic way, it's called pulse modulation. You start with a pulse waveform. And this is what the pulses actually look like, something like this. And you take your bits, and you modulate them into a real number. So a 0 goes to +1, a 1 goes to -1. Okay? And then this value that you get from your bit value, we call that the modulation symbol. You take the modulation symbol, you multiply the pulse by it. So in this case, I would be just taking this pulse or flipping it. And then you do that in a train. So in this case, notice that this pulse is 1 here, but at each one of the unit times here, so this could be microseconds, or this is a normalized time. At +1, +2, +3, it's a 0. So when I add up these, so the idea here is that the red dot is the same. You see, what do I have? 0, 1, 0, 1, 1, 1. Okay, 0 is a +1. -1, 0, that's a 1, which modulates to a -1. 0, 1, 1, 1, 0, and so on. And you modulate each one of those pulses, and you add them all up, and that blue line is the signal that you get. And if I can sample right at those instances, so there is a synchronization problem. I'm not going to talk about how we get the timing synchronization. Again, it's just a bridge too far. But if I can sample right at those points, then the value of the signal is exactly the modulation symbol, which I can recover. And then, yeah, okay, I'm not going to get this pristine signal back. I'm going to get this plus noise. So what are you going to do? You're going to take the sample, and you're going to say if it's bigger than 0, call it a 0. If it's less than, if the sample is less than 0, call it a 1. So that's basically, I don't have the signal plus noise picture, but I think you can visualize noise writing on top of that waveform. So it's basic pulse modulation. You can say, well, why don't you just use a rectangular pulse? That might be a natural. And the picture would be so much easier to look at if it was a rectangular pulse, right? Well, the problem with that is rectangular pulses are spread out in bandwidth. And we have to be efficient with bandwidth. We have to be efficient with everything. So this type of pulse is actually a rectangular pulse in bandwidth, in frequency, not in time. Okay? So then we got to get, so we've gotten from bits, so we've done a lot. We've done source coding, we've done channel coding, we've done digital modulation, and now we're going to do digital RF modulation, but that's easy. Just think of RF modulation as being digital pulse modulation in the baseband plus either DSB or FM. So you got, this is not important, but the FM version is GMSK. The nice thing about the FM version, though, is it has that constant envelope to it. And we'll see why that's important in just a second. And then you have these linear modulations which are based on DSB. Okay. Now, one more thing before we get to the 2G. Let's see, how am I doing? Okay, good. 20 minutes. Just about right. Okay. What happens when we send this over the channel, over a cellular channel? Well, there's a couple of things. You get noise interference. Okay, the interference, I already talked about the cellular interference that you're going to get from cells using the same frequencies. There's also thermal noise in the circuits, okay? But now we also have these distortions. Multipath and Doppler. That's supposed to be shifts. Sorry about that. Okay, Doppler frequency shift. Okay, so I'm not going to explain the Doppler phenomena. I hope you maybe had it in high school or something, but it's basically when you are receiving or transmitting from a moving vehicle, from the velocity. If the path length is getting shorter, then the carrier waves are getting compressed, and you get a higher frequency shift. Okay. All right. So this is kind of what this picture, just think about this picture right here. So I got my cell tower, I got a bunch of scatterers, and I got my mobile vehicle. And so I have a direct path, and I got all these interferences. This is the multipath. Now, we're using the PDF version. I had some nice animations on here, so I'll just stand over here for a second. Does anybody know what the speed of light is?
3 times 10 to the 8 meters per second.
Wrong. Anybody else? That's cheating. Okay, so you learned something today. The speed of light is a foot per nanosecond. Okay, foot per nanosecond. If you remember that, then this picture all of a sudden is going to make a lot of sense. Why? Because you can see just your notion of geometry, that you have a path here and you have this path is longer. Well, roughly how much longer? Just from your notion of geometry, if you're in an urban area, it might be a couple hundred feet, 500 feet, maybe 1,000 feet. That would be a long one. The multipath delay then is just going to be 1,000 feet. It's going to be 1,000. It's a microsecond. Okay, so you get a microsecond of delay for every 1,000 feet of differential propagation. Okay, so this really pays off. And another thing is that if you ever, how do you relate wavelength to carrier frequency? Okay, well, the wavelength at a gigahertz is 1 foot. You know that right from that. So it's just a real useful way to think about the speed of light, and that's the way they should teach it in schools. Okay. But, okay, so we have this multipath problem, and that's going to be a problem for us because I just went through this whole pulse modulation. Now if I take that signal and I have echoes, right, because all multipath is echoes, then that property of sampling it just at the right time and extracting just the one value, it's not going to work anymore. So I'm going to have some sort of equalizer to get rid of the multipath. So we talk about the multipath in terms of one parameter is the delay spread, which is the maximum minus the minimum. So just because we know what the speed of light is now, delay spreads for indoor, like in wireless LAN, 50 nanoseconds, 100 nanoseconds. Urban environments up to about 2 microseconds. Suburban, rural, hilly environments, you can get up to like 20 microseconds of delay spread. Okay, so you have delay spread. Then you also have this problem, the Doppler. So you know what Doppler is, but notice Doppler frequency shift, it's a positive shift if the path length is getting shorter. And it's a negative shift if the path length is getting longer. But each one of these paths is different in that respect. Here, this path is getting longer, so it has a negative frequency shift. And this path is getting shorter because the car is going in that direction, so it has a positive frequency shift. So Doppler is not just one shift, it's a whole bunch of different shifts. Okay? So what is that going to do? That's going to make our job really hard. In particular, Doppler leads to fading. Doppler and multipath together lead to fading. And I'm just illustrating that with this simple example. I took 2 sine waves. the red and the blue. And they're slightly different frequencies. That's all there is. And then I add them up and they get the black. And you see in here, the two sine waves are in phase, so when you add them together, you get a bigger amplitude. But over here, they're out of phase. And that changes with time. So you can see the fading is going like that. So I have to deal with a channel that is fading in amplitude. Okay? So, for example, I mentioned that the analog systems used frequency modulation, because frequency modulation has a constant amplitude. Okay? Well, frequency modulation is also robust with respect to fading, because I can take the signal, it's been faded now, so the amplitude's gone up and down, okay, with the fading, but I can run it through a limiter and get back a constant and then after I get back a constant amplitude wave, I can send that through a frequency discriminator and demodulate it. So FM is naturally robust, and that's why they use FM. Okay. So, okay, so this is showing kind of realistic fading phenomena. This is in time, so this is about 200 milliseconds worth of time, and this is probably be for a vehicle that's going at about 60 miles an hour, something like that. You also have fading in frequency too, so you know, just without getting into the details, we call this frequency selective fading, and this is time selected fading. In reality, both are going on at the same time, so here's a nice little chart with frequency versus time, and the channel is just a mess. And all I want you to do is think right now that how do you ever communicate over something like this? Okay? But that's the challenge that we have. Okay, so now 2G. Okay. I might go 10 minutes over 1 o'clock. Is that going to be a problem? Yeah. Okay. Okay. So the first 2G was the introduction of all digital. So using all the stuff I've just been talking about. Time division, multiple access. TDMA, what do? You take time and you divide it into frames, and you divide frames into slots. And then you assign users time slots. Okay? So now, a channel in a TDMA system is actually two components. It's a time slot within a frame. Don't worry, I have pictures of this in the next slide. It's a time slot and a frequency channel. So really, TDMA systems were hybrid TBMA, FDMA systems because they had time slot frequency. Okay. So now we think of a channel as a pair, a frequency and a time slot. Okay. There were two standards. The first one was the AMP standard, and this is the one we had in North America. It used the same 30 kilohertz channels as the AMP system, so that they could have the D amps. They called this digital amps. Amps was the 1G system, and they could have towers that were simultaneously doing analog phone calls and digital phone calls over the same bandwidth. All you'd have to do is in the control part, you'd have to signal, "Hey, I'm a digital phone. Give me the digital signal," something like that. Okay. Used the same bandwidth, but it used 3 time slots per frame. So in principle, it had 3 times as much capacity as the amps, because for an amps telephone call, you're giving the user the frequency channel continuously. And for the digital amp, the TDMA, you're giving it just 1/3 of the time. Okay? Then the second one was GSM, which was the European version of this. And they said, forget about the analog stuff. We're not going to try to get any type of backward compatibility. We're going to do something different. So they made the bandwidth bigger, and you're going to see in a minute why making the bandwidth bigger is a good idea. But since you have more bandwidth, you're expanding. You want to think about capacity as being a two-dimensional thing. It's bandwidth times time. Okay, so if I increase the frequency bandwidth, I can have smaller utilization in time. So they have 8 slots per frame. So this is what this looks like. And now I'm sort of pulling things together now. again, unfortunately, if this was the keynote presentation, this would be, these come in later as animations. So don't look at this yet. Okay. Just look at this part. Okay. So it was designed around the speech application. So I had these speech encoders, and every 20 milliseconds, the speech encoder is producing roughly 200 bits of speech data. Okay? And then I'm going to take the 200 bits and I'm going to encode them with the channel code. That adds the redundancy that's going to give me resilience, and that's going to be called, so that's 300 to 400 bits per coded block. But so I have this train of blocks that I'm transmitting, okay, over the channel. Well, what you do down here, this is the frames. These are the GSM frames. A GSM frame is 20 milliseconds, so time is compressed here, okay? But it's divided into 8 slots, so each slot is only about a half a millisecond long. So the slot that this user gets within the repeating frame is the red line here. I have this expanded on the next slide so you see that a little better. Okay, well, each one of these slots can carry about 100 bits, but I've got 400 bits of information. So what they do is this 400 bits is spread out over 8 frames. There's a little, I call this dovetail interleaving, you know, because the next block starts up and its bits go over. So each one of these slots is carrying about 50 bits from one speech frame and about 50 coded bits from the other speech frame. So each speech frame is actually spread out over 8 slots. Okay? So why would you do that? Look at the fading channel. Okay? So this is just that same picture before I just stretched it out. But actually this is not, this could be typical. And what I've done here is, like, for this particular, this is teal in color, for the teal block. It got transmitted over these 8 frames. Well, during that transmission, this is what the fading pattern looked like. And so those slots are going to sample that fading pattern. That's what these teal dots are, here, here, and here, and here. And see, what happens is that the 8 frames, out of the 8 frames for one that trace back to one speech frame, right? Most of them were okay, but there were a couple that hit these deep fades. Okay? That's where the power of the channel coding comes in. Because I'm not going to decode the slots. At the receiver is going to demodulate this data for each one of those slots and then put it back into a set of observables to decode the whole block, the FEC block. FEC, if I say that, that means forward error correction, but it's the channel coding block, okay? So the information that the channel coder is, or decoder is going to use is spread out in time. It's spread out in time over those fades. And so the fact that you know, 1/4 are deeply faded, I can still probably decode because I still have enough good slots that the decoder can overcome that and reproduce the speech bits as transmitted. Does that make sense? This is called time diversity. We're dealing with a situation where the quality of the transmission source is uneven. And so what we want to do is take our information and spread it out over time after channel coding. It does not work unless we put in this redundancy of channel coding. That's the key. So that the coded bits, some of the coded bits are going to be exposed to bad situations, but in any given block, not all of the coded bits will be exposed to. And so the decoder can recover. Okay? That's how information theory works. Okay? And it's actually a combination. If you think about it, this whole scheme here, it's using both the source coding and the channel coding and the modulation and frequency aspect of this thing. So, okay, so here's zeroing in a little bit more on the TDMA frames. Like I said, 20 millisecond frames, half millisecond slots. Here's one frame, one slot. The slot is just really just the unit of time we call the actual signal that's transmitted a burst. And it looks like this, just details, right? But you have 58 information bits, training sequence. You got to have a training sequence because I got to do all this signal processing to demodulate. That means I have to estimate what the channel looks like. And I can't estimate the channel unless I have some channel sounding bits. So that's what this is. Okay, but that's a big deal. Okay. The fading, so the GSM symbols, these bits here, each bit corresponds to one symbol. These are coming at 3.7 every 3.7 microseconds, which means that when I was talking about delay spreads, okay, the delay spread is a significant chunk of the time between adjacent symbols. So the multipath is going to affect the demodulation, and we're going to have to do signal processing to take care of that. Okay. All right. Now, this solves a big problem. We've got cellular frequency reuse solved a big capacity problem. Time division multiple access gave me resilience against time fading using time diversity. But there's two more problems that I haven't really addressed yet. One is that I could still get interference from all these other cells in this cell right here, okay? And if this interference happens to be a strong interferer just because the propagation conditions were good, okay? So he's a strong interferer into my call. It's going to hit every one of my slots. It's not like the fading, because the fading only hit a couple of slots. The intercell interference potentially hits everything. Okay, so that's a problem. So that's intercell interference. Yeah, okay, so that's what I just said here. And then we have another problem with the slots. The slots, you see, the slots is a resource reservation. When you make a call, you get the assignment of a slot and a frequency channel, right? But like I said at the beginning, is that voice activity is really about 50%. And you've assigned that resource to a user even though the user is not using it half of the time. So that's another problem, okay? So how can we deal with that? This is the slide you've all been waiting for. Hedy Lamarr. Everybody remember Hedy Lamarr? How about Hedley Lamarr? How many people know Hedley Lamarr? Okay. So your homework is to go and watch Blazing Saddles. Go get it off of Netflix or something. But this is Hedy Lamarr. Hedy Lamarr was a actress from Austria, and she was Jewish, and she fled the Nazis and came to America. And she is an excellent example of a woman who's both beautiful and brilliant. She invented this scheme that's called frequency hopping spread spectrum. And it was patented. It did not actually get deployed in World War II, but she had a patent on it. And she had a co-inventor, George Antheil. And so this is how the story goes. Let me see what. Okay, just 10 minutes. I'll cut it off at 10 minutes. Okay, the story goes like this. In World War II, they had these radio-controlled torpedoes. And you're thinking, what does this have to do with GSM? A lot. And so basically, you know, they'd launch a torpedo, and the torpedo would have a little antenna sticking out of the water, and the guy on the ship would have like a joystick, probably not a joystick, but some sort of controller, and he'd say, go left, go right, go left, and try to steer it to the enemy ship. Well, the enemy figured out that, hey, you know, they're using radio-controlled torpedoes. All we have to do is get a bigger transmitter and jam it. Okay? Well, George Antheil was a symphony conductor, and he had put together this, this performance piece with 12 player pianos. And he got it so that he applied just, you know, the old-fashioned player pianos that had the air, the paper rolls with the holes in them. I know you know what it is, Tom. But you know, it's these old player pianos, and they got the player pianos synchronized by getting them to run exactly at the same speed, and they put together a concert with 12 player pianos. So Hedy Lamar's idea was, well, if I can do that with a player piano, then I can do that with radio frequencies. Okay, so what I'll do is instead of transmitting at one frequency, I'll hop my frequencies around. And then, yeah, the enemy can jam one of the channels, but he's not going to be able to jam all the channels all the time. Okay, the patent was actually to use little player piano rolls, and one would be in the torpedo, and one would be on the ship, and that would synchronize the transmitter and the receiver, because you know the transmitter's hopping frequency, the receiver also has to hop its frequencies as it's going along. Okay, so it knows where the signal is, and you get those synchronized. Great, solves the torpedo problem. Okay. Again, it's kind of this robustness. It takes this one channel where everything was concentrated that was easily jammed, and by spreading out over frequency, wider frequencies, we've turned this into a hide-and-seek game now. So you can see, it doesn't take much thought to see how there would be lots of military applications of this. Okay? But at any rate, the basic idea of using a much broader spectrum to transmit your signal than the actual original spectrum, this is called spread spectrum. And frequency hopping was used in GSM. And it's also another form of spread spectrum is called CDMA. And you've all heard of CDMA phones, right? Similar concepts, but it's a different type of spreading. We'll get to that next time if there is a next time, okay? So, so this is showing the problem. So what you do in GSM is you have these time slots. Remember, a time slot is a frequency. A channel is a frequency and a time slot. Well, now a channel is a frequency hopping sequence and a time slot. Okay? So in these signals here, so this is time and frequency now. I've got three types of signals going on here. The red signal, this is the guy, that's our phone call. That's the desired signal. That's our phone call. The blue is another phone call from the same tower. If it comes from the same tower, it's naturally already synchronized. So you see how the red and the blue, they're lined up here. See, the red and the blue are always in the same slot. And not only that, but we can be smart enough in the way we design our sequences to make them orthogonal, meaning that they'll never collide with each other. Now I can do that when I have transmissions from the same point, like the same cell tower. But when you go to the other cell towers, that's the inter-cell interference, that's where the problem, the synchronization and orthogonality goes away. And the reason is because there's a propagation delay. So even if I had them synchronized at one point in space, in a different point in space, the propagation delays are different. They're not. And if you look closely, you see here the yellows and the greens are not lined up with the reds and the blue because they came from different towers. And you see what happens then is, so there's like a randomization, and every once in a while you see the green and the red collide. And over here, a yellow and a red collide. So those would be. But, so I've taken, what I've done now is I turn it exactly back into the same problem I had with the time fading. I'm transmitting each speech frame gets encoded into 400 bits, which gets distributed across 8 blocks. Okay? And now the interfering signals might hit me once in a while, but they're not going to hit me all the time, and therefore the error control coding can give me that robustness back. So this is how, you know, the first example of how spread spectrum, multiple access. And the reason why it's multiple access is because I have a hopping sequence per channel, but different channels have different hopping sequences. So the yellow is different than the red is different than the blue, and so on. Okay? Well, that's it for today. So this is the rest of what we need to go through. The CDMA, I just mentioned that. This was this continuation of the 2G. WCDMA is considered to be the first 3G, that's wideband CDMA. A little bit about wireless LAN, and in wireless LAN I talk about the triumph of not scheduling. And then we'll get into the multiple antenna stuff, where now we get more capacity by using multiple transmit antennas and multiple receive antennas. Why in the world would you do that? But it's very popular. It's used in wireless LAN and it's used in LTE. Okay? And then 4G, which is LTE, which is the triumph of scheduling. So this is the polar opposite of this in a big major sense. So if you all decide to have me back, that's what we'll cover next time.